my name is Doverspike, and I'm an aerospace engineer who develops rockets, hardware, and products for the DoD, National Science Foundation, and other private companies. And that explains why a lot of this presentation will be fairly heavily focused on the hardware side of these things. However, don't worry, a lot of the focus will also be paid attention to the software. So, without further ado, welcome to my presentation on getting started in reverse engineering and how to get your students interested in reverse engineering as well. So, what is reverse engineering? Well, if you own a Nintendo Switch like I do, you probably already know what these things are. These are Nintendo Switch Joy-Cons. And you also probably understand why I'm so frustrated with these things, namely joystick drift. And if you're like me as well, you've lost far too many games of Smash Brothers because your character decided to side B rather than neutral B. And if you don't know what that means, that's okay. It just means that the game wasn't doing what I was wanting it to do because the controller lied to the Switch about what it was saying that I was doing. So there's a couple different ways that we can go ahead and fix this issue, and many of which involve reverse engineering. Pretty much any way of solving this problem, aside from buying a new one entirely, involves some degree of reverse engineering. So what is our first option? Well, for this presentation, the first option is going to be replacing the specific part that has failed. And in this case, it is the Joy-Con itself. So the simple solution is just replacing the little part. However, there's still some complications with this. So for better or for worse, replacing this component with the OEM one, you're replacing it with a faulty component. So whenever you fix it, it's only going to be fixed for so long. So for better or worse for here, because Nintendo and its OEM Hoseiden have decided to keep this part as a close to their chest and not releasing replacement parts to the public, as unfortunately right to repair is still only just taking hold, we can't actually buy the OEM component. So we have to find some sort of light component. So there's a few barriers in a way, but luckily for us, we have a mostly working part. And this allows us to figure out pretty much everything we need to know. It gives us the pinouts, the neutral values, the minimum and maximum values, as well as the physical footprint. Everything we pretty much need to know in order to find a like replacement. So from there, we can go ahead and read the data sheets of similar components and find one that works. So we were able to take the problem that we had, use reverse engineering to figure out everything that we need to know for the design requirements for a replacement component, and find one that works. However, luckily, most third-party manufacturers have developed a replacement drop-in part, which saves us a lot of the work on the back end. So, what if we decided that we want to build a new one? So, building an entirely new Switch Joy-Con is a little bit out of the scope of this sort of project. So let's go with something else that I kind of enjoy, which is RC cars. So let's say you get an RC car for your birthday. Yay! But, oh no, you accidentally drop it into a lake. Well, it got into the lake, and by no fault of your own, definitely by accident. And unfortunately, pretty much everything except for the frame itself was destroyed. But because you have the frame and some of the other components, you want to see if it's cheaper to either build a new one or do a rebuild. So, what is reverse engineering? Reverse engineering is looking at something, breaking it down into its core systems, and building it back up again. Next, you're basically going to be using previously designed systems to design, build, and improve additional systems to your preference. So, what do we want to make it better? Well, it gives us the opportunity to take a look at what we didn't necessarily love about our previous toy, RC car, and say, okay, we wanted to have better range, we wanted to go faster, and we wanted to go cleaner. But how do we go about solving these problems? Well, let's go ahead and start by thinking of all the different systems that make up an RC car. So, what are the different parts that we need? First, we need to be able to make this go. And for that, we need a motor system and all the different components involved with that. Next, we need, because we want it to go more than forwards and backwards, it's not a train, it's a car, we need to have some way to steer the system. So we need to have a servo as well to control. Next, we need to be able to control everything. We don't want to be having to push everything, we want to be able to be a little ways away and go faster than what we can. So we need to have some sort of radio system to be able to communicate with everything. Next, we need something to be able to control the entire thing, which we're going to be using a microcontroller system for. Finally, you need something to power the entire thing, and so for that we're going to be using a battery system. Well, it might not be too bad with a simple system like this to figure out all the ways that the systems interact. I always find it really helpful to put everything down into a diagram. So let's look at the way that we can engineer these different systems. So I found that this flowchart here seems to be true for most every system out there. So you have a sensor that receives a control for someone or something outside, or use sensors to figure out something about the world around it, be it temperature, position, orientation, etc. Next, you have some sort of processor to take that information, combine it with preferences and algorithms, and then that input, that processor takes the input from the sensors and gives an output to whatever control systems that you have, be it either flaps on a plane, the motor or servo on an RC car, or maybe some terminal somewhere. And of course, pretty much every system needs some way to power it. So let's go ahead and apply this to our example of an RC car. So first we have a radio, which receives all the different commands from our radio that we are holding. All the information gets given to the processor, and that processor takes everything using different controllers like PID controllers, other software mechanics, in order to break everything down to all the different outputs in a way that each one can understand. So it takes that information and converts it to a pulse width modulated signal and sends that signal to the motor ESCs as well as the servo. But this is still kind of a little bit abstract for my preferences, so let's go ahead and turn this into photos. Here, this is where I find things that become really tangible. So at the very top, we have the radio system itself, which is built into the controller. And luckily for us, manufacturers have planned everything out and improved things over the past several decades to make things fairly simple. So that controller has all the necessary outputs to send the correct signals to the ESC as well as the servo in order to make sure that the car is going in the way that you want it to go. And of course, the whole entire thing is powered by a big old battery. Setting everything up in this sort of fashion can help a lot with coding as well, not just the mechanical parts, as it provides a visual flow not only to how the system as a whole will operate, but also the way that the systems will interact in code as well. And this will be demonstrated a lot more further in the few slides down. With that, let's go ahead and get started with getting students interested in reverse engineering. So now that we have a better idea of what reverse engineering entails, let's go ahead and start talking about how to get students interested in reverse engineering. And the best way of doing that is doing something that's associated with their interests. If they're interested in planes, you build an RC plane or something like that. If they're interested in robotics or with reverse engineering code, you do something that focuses entirely, not entirely, but focuses heavily on what they're working with or what they're interested in. Next, it's goal-oriented. You want to be able to build an RC car with such specific requirements. Say you wanted to go 20 miles an hour, you wanted to be able to run for 20 minutes, you wanted to be able to operate out at 1,000 feet. These are giving students goals allows them to focus on ways that they can improve everything and work in a way that works best for them. Next, you want to have some sort of clear success criteria. So for example, all the programs are working as intended. Not only are you able to reach 1,000 feet, you're able to reach 2,000 feet. Just again, focusing, having some sort of guidelines that the students can follow to give them the opportunity to figure out, okay, this is what we need to work towards, and using the different systems to be able to figure out how they need to code it, how they need to build it. Next, you want to have clear checkpoints throughout the project. Not only do you want to have the final product, you want to have kind of design reviews midway through. You want to have kind of checkpoints to where halfway through the project they're able to move the car forwards and backwards, not necessarily have to work on the steering yet, but you have, say, at one point you have independently the move forward and backward motion. Next, you want to have independently the left and right turning of the servo. And then finally, you can put all of these different things together. Breaking it down into smaller systems allows students to kind of focus on one problem at a time and not to get too overwhelmed or too frustrated with something, as a lot of times it's a lot simpler to troubleshoot things whenever you know all the previous stuff works and then you introduced a new system and it doesn't work then. Next, you want to hit on multiple disciplines. You don't want to focus on just mechanical, just electrical, just software, or just the arts. You want to have incorporating a decent amount of all of the above. This allows students to not only get experience on what they're interested in, but it also gives them exposures into things that they would not necessarily have thought about previously. So for example, whenever I was first interested in aerospace, I thought, okay, I'm going to be designing UAV airframes. Whenever I was in college itself, I got a lot more exposure into rocketry, and I'm like, it'd be really cool to be doing nuclear propulsion rocketry. And now I'm really into test, and so working with systems, making sure everything works properly. And through exposure of these different things, it made me realize I had a lot of interest in a lot more than just what I thought. Next, it's flexible to best fit student interest. You don't want to force them to focus on small little things if they're really disinterested in it. That's a really good way of getting them to shut down and not become interested in anything. Allowing them to kind of choose their own path to create these projects is really what this is about, allowing them to figure out what they're interested in so that they then can later go in and deep dive into these different subjects. Next, you want to have flexible definitions of success. The goal here is learning, not an end product. Because they're not working a job, you don't need to make sure that they have the exact deliverables that you need. Say, going back to the RC car example, say you're only able to go 500 feet. Sure, it technically failed to meet the original deliverable. However, they got the experience doing everything that they were doing, and that really is where the success in these different projects lies, is getting the students exposure and experience with these different things. Finally, you want these projects to be difficult, but not frustrating. Challenge is good, however, anger is not. As soon as your students start to get to the point where they are becoming angry with whatever they're doing, is wherever they begin to shut down, and anything beyond that is not productive. So keeping it in the challenge and productive portion of the project is really, really essential. So let's go ahead and look at what make a few good first projects. And in my experience, first projects kind of have the following attributes. First, they're curated. The projects are a lot more like Lego than a kit car. And the tools for success, you have everything that the students need in order to complete the task around them within arm reach. This allows the product to have a decent amount of flexibility, allow for student creativity to maybe apply things in ways that you didn't think about. So for example, in the home AC thermostat lab that we're talking about, maybe you have a potentiometer and they decide rather than hard coding all the preferences into code, they use the potentiometers to choose the temperature that people are comfortable with. Next, they're interactive. They have some sort of tangible indicator of success. And for the first projects, the more hands-on the project it is, the better. One lab that we'll be showing as well in the future is a Ohmmeter Lab, where the students are able to take the lab and probe different parts of the microcontroller and figure out the different voltages. And they can actually use this to kind of figure out where the different traces go as well. And not only that, within this lab they have the ohmmeter itself, so they can also figure out, okay, is this trace actually connected to this other portion of the project? And so they're actually able to start developing their own schematics and reverse engineering the hardware as well. So having some sort of hands-on, I always find is great because they can see immediately as they're developing the code that what we're doing is working. I'm doing something. Next, simple, not easy. Too easy is boring and you'll fail to keep the student interest. Striking the right medium can be a little bit challenging, but it is very, very achievable given thought and looking at the experience of whatever students you're working with. Next, it solves a problem. It doesn't have to be a real problem. You can come up with it on the fly, or you can have previous examples from earlier in life. But having some sort of problem to solve gives a dramatic increase to the reward of success that the students get. And not only that, it encourages them to look at other problems and different things in their life and say, can I actually fix this? What would it take to fix? Finally, these projects can be collaborative. They either can be with you, doing some sort of design reviews, preliminary critical design reviews, post-flight reviews, or it could be with a group of other students where you have a team of students working towards to complete some goal. But having a collaborative effort allows them to get experience kind of writing write-ups to it or working with teams. So when working on projects with students, it's important to give a couple different reminders so that the students don't have to worry about whatever concerns that they might have, that they're able to entirely just focus on what they're doing and be able to become as successful as possible. First, it is okay to have things break in the pursuit of knowledge. This is especially important for girls students because in our experience working with disassembly labs of computers, you'll see that the boys always kind of dive right in and the girls tend to sit by the sidelines. And whenever asked, why aren't you going in? Why aren't you working on it? A lot of times you'll hear, I'm worried about breaking it. I don't want to break it. So encouraging students up front that as long as you're working on the project and not intentionally breaking things, it's okay for things to break in the pursuit of knowledge. Next, failure is always an option. As long as the students get in, get some experience, and have some sort of lesson they take out of everything, the learning is the success that these projects are intended for. Finally, controlled chaos is okay. Lab space is a dedicated space for mess, so keep it confined to that area. And we'll go ahead and get to this in the next slide. So having some sort of activity in lab space is super duper important because it allows students to have an area that is created chaos of creation is allowed. So it doesn't have to be super fancy. It doesn't have to have thousands of dollars of equipment. And as I alluded to a little bit earlier, students can actually develop their own hardware for this as well. But having some space where they can have their mess keeps the mess in the area and prevents the anger and frustration of both the person who's responsible for the area as well as the student. So let's go ahead and look at some of the first examples that I tend to use, and especially the JROTC Cyber Command lessons on reverse engineering that I've developed. First off is the replacement volt ohmmeter. The scenario is, in the middle of one of the projects, your multimeter died on you, and the special new battery will take a few days to arrive. And you have to use the tools at your disposal to create a tool to measure voltage and resistance so you can complete your project on time. The equipment utilized in this lab is going to be a microcontroller, resistors, wires, and a breadboard. The goals for this lab is to get the students to work with analog to digital converters, voltage dividing circuits, and outputting results to a terminal. The next one is a broken AC thermostat where, in the middle of the winter, the AC thermostat went out. Luckily, you have everything at your disposal to be able to create a new one in order to tide you over while you're waiting for the new one to arrive. Or maybe you'll decide to stick with the better one that you made. The equipment available for this lab is a microcontroller, thermistor, RGB LEDs to simulate the AC system itself, resistors, wires, and a breadboard. The goals for this lab is to work with analog to digital converters, thermistors, controlling an output, and optionally using PWM to control the intensity of the output. Let's go ahead and look at these in kind of a systems output. And this can kind of start to show you how not only the system is useful for the hardware side of things, but also the software. You can see that from the top, you have your ADC readings, which tells you, okay, I need to have these different things declared, and then I also need to be able to read it in. Next, you have the processor, which takes the information read in and processes it in a way that is useful for the output. And in this case, we're specifically printing the voltage to the Thonny terminal, which can be shown in this next video. In this video, you can go ahead and see where we're going to be using this probe to probe different portions of the board. The first one is the middle of the voltage divider, which shows you about 1.3 volts. And the next one is going to be the output from the Pi Pico, which is about 3.3. And finally, it's going to be the USB, which is about 5 volts. Next, let's go ahead and take a look at the AC thermostat that was discussed. And not only does this help you with the code itself, it also dramatically helps with writing pseudocode. So again, reading in from the thermistor, which is an ADC, you first declare it and you read it in. This code here is actually given to the student because it's the specific thermistor equation, and it's basically the same information if they were to just Google it. So providing them can sometimes be helpful and reduce a lot of frustration, so they can focus just on the logic of the system. So from there, you go ahead and process the information in these portions, and then you print out or control the RGB LED in the rest of the system. And we can go ahead and show this in the video here as well. So you can go ahead and see where neutrally it's one color, but as soon as you put your fingers on it, it goes to neutral with no output, and then it goes into red, which means that it's going to be cooling. Whenever you remove your fingers, it takes a little bit of time, but it eventually gets to the point where it is then doing nothing and then heating again. So what do these projects have in common? On top of solving problems, these labs have a single input to give a single output, are simple to troubleshoot, use the basics of coding, electronics, and problem solving, and are especially interactive. So for the volt ohmmeter, you're physically interacting with the wire, and it changes the output to show what's being measured. The AC thermostat, the LED changes color depending on whether or not it's being held. Additionally, both of these projects are especially easy to build upon. ADCs are especially used very commonly to measure different sensors. And the general outcome, the general process of coding, is basically going to be used anytime that you're going to be doing development. So let's talk about building on projects. And while these next two projects might be an overfit, it allows students to focus on one problem at a time by design. The first one is a timer-based stoplight, where you just have a time-based stoplight system. There's no the only input is the timer. You don't have any sort of sensors. So for the equipment for this is a microcontroller, resistors, wires, breadboard, and RGB LEDs. And the goals for this lab is to work with timers, multiple outputs, and working with sequences. Building upon that, you have an active stoplight where, say, depending on an increased demand, you have to be able to increase the efficiency. So you need to use a sensor. For this, we'll be using a Hall effect sensor to measure a magnet as if it was a vehicle. For this, the equipment for this lab is a microcontroller, resistors, wires, breadboard, RGB LED, and a Hall effect sensor. And the goals for this is to work with timers, multiple outputs, sequences, stateful programming, analog to digital converters, and Hall effect sensors. Looking at the different two systems diagrams, we can see that they're pretty much identical, aside from the addition of a Hall effect sensor. Some additional coding will be changed in the processor as well, because your input has changed as well. So let's go ahead and take a look at a video of how this looks. So first, our first example of just a timer-based system, you can see how it just over time changes colors. However, whenever we apply the second code base, where we now have the input of the Hall effect sensor, we then take the magnet here, take it close to the Hall effect sensor, and you can see now that the light turns green, and it will remain at green indefinitely until you remove it away. So let's go ahead and talk a little bit about software reverse engineering. Not to leave out software reverse engineering, capture the flags are a fantastic introduction that often have write-ups and guides explaining all the necessary steps should you not have the necessary experience or time to be able to go through everything. I really enjoyed Google's Beginner Quest, especially the Challenge 1, which is their CCTV reverse engineering lab. And the reason why I like it is because the code is simple to understand, but it still requires some problem solving. So taking a look at the very beginning, you have a couple different changes that are done to an input, compares it against an array, and then a check is done. There are two variables, one that grabs the password from the element, and another that looks at the array. And let's go ahead and look at the second line a little bit more closely. So we can see that the password is hashed and modified with the addition of cafe. And the array shows that the password is 12 characters long. So simply by placing these in the correct order and then converting to an array, we already simplify this very significantly. And we're able to take this and undo what the array has done. So for every example, we take the value in the array, subtract cafe, and we get the result of good password, which, when entered into the password, gives us the flag and shows that we were successful in a reverse engineering journey. So let's talk about next steps. Now that your students has accomplished their first steps, they're likely looking at how to advance their projects. So the best way of doing so is building on prior projects. By reinforcing and reusing code that has been done previously, you're showing the students that their knowledge is useful, and it shows to them that they can remember and do things. Then it increases complexity. For example, multiple inputs or multiple outputs. Say you have a 6-axis IMU, and you're trying to figure out the position of it so that you can use that to control a quadcopter. A little bit complex for a second project, but it's a good example. However, you don't want to just add complexity for the sake of complexity. You want to have purpose for it. Next, it incorporates more real-world projects. Robots are cool, and having something that interacts with the real world, especially if it does it autonomously, are amazing. And being able to show the students that they can build things that change things in the real world are a fantastic way of keeping them interested and making them want to move forward in their reverse engineering journey. Next, these projects are cooler. As time goes on, because you can have additional complexity layered onto these projects, it allows you to make things more complex, which a lot of times allows you to make projects cooler. And it allows you to focus also on students' interests, be it mechanical, electrical, or software. And additionally, say that someone's really interested in planes. You can go ahead and have them where they design and build their own airplane using their own software. Optionally, and this is the one that I actually really enjoy, is some sort of competition. Competition is a great way to keep and demand student interest and attention. So let's go ahead and talk about some of my favorite competitions and projects. I got my first start with First and Best Robotics, which is a middle to high school robotics STEAM competition, which also includes the arts portion, which is a booth that shows off your project. And basically you're trying to sell your robot to the investors around. Next is the Mate International ROV competition, which is a high school underwater rover competition. Finally, you have the NASA Human Exploration Rover competition. And one great way to get students interested is even just mentioning NASA. More on the project side of things, capture the flags are a great way to learn about coding, and especially software reverse engineering, especially in a confined environment to where they can do things safely. Next, robots. Problem-solving machines are, again, really cool that they get to interact with the things around them and problem solve. And being able to get students working on these different things to solve problems, you can just see how excited they are. The next is RC toys, which we've kind of gone over a lot. And I find these to be a lot better than buying things off the shelf, as it allows them to get more into it and understand everything a lot better. And finally is real-world problem solving. Whenever I started thinking about things in this way of the systems design, things become a lot clearer, a lot simpler. And I found that solving my problems, say my washing machine was broken, and the problem was that it was failing to measure the spin. So I can actually go in and figure out what's wrong and fix it. And that's, I always find to be very rewarding, and honestly, it's really great. And the last thing I wanted to include on this presentation is the parts list. For all of these different labs, the total cost of them was just a little bit over $12. While doing some sort of output, working with robotics is going to be a little bit more expensive, it doesn't have to be that expensive to get students started and working with these things. It's really quite affordable. And so I hope I have encouraged you to kind of go out and hopefully taught maybe even you a few things about the process of reverse engineering, so you can go ahead and take this and educate others as well. And I've always found that teaching others is the greatest way to learn, so I hope you are encouraged to go out and do that. Thank you, and I hope you have a great rest of your day.